Now, with the properties of these op-amps that we have described, keeping that in mind, we can make many useful circuits with an op-amp. Like we can make some voltage amplifiers. So we will now discuss voltage amplifiers, how to make voltage amplifiers with op-amp. Okay, so we can make many useful circuits. For example, voltage amplifiers are some examples of that. We'll see how to do that. But before that, let's consider what will happen if I take a op-amp and then it has two inputs, plus and minus, and so I have to give some input supplies, input voltages to these terminals. So what I do, I connect it to a voltage source which has a value, say Vp. So this is a fixed voltage, the other end is grounded, so this point is at 0 potential, this point is at Vp potential. This is the output. I have to give another supply, I have to connect another source of voltage, source of potential here. Now what I do, I being very crazy, short circuit these two terminals. Okay, so this is VO, V output. So I say I don't have any more source of voltage with me. I say the op-amp, take your own output and feed yourself back as your other input. Okay, so I needed another output Vn, but I'm running out of any more source of voltages. I have only one source of voltages in my laboratory, which I connected to this terminal. I have no more source of voltages, so I say the op-amp, do one thing, take your own output and connect it to your input. Now what will the op-amp behave like? It's a crazy connection, isn't it? What will be the output? So now let me ask the question, Vu is equal to what? What will be the output in this case? Say if I say when Vp is known, okay, when Vp is known or given to us, say I tell you that Vp is 5 volt, tell me what will be the value at this output. But I cannot tell that, because to know the value at the output, I have to compare these two inputs. If I know which one is higher, then I can say what the output voltage will be. But to compare these two, I need to know the value of both of this. This one I know, this one is given to me, but this one I don't know, because this one depends on the VO itself. So which means to know VO, I need to know Vn and Vp, and to know Vn, I need to know VO. So this is a chicken and egg problem. Right? So I cannot, so the question that I ask, what is the output voltage? But I cannot say that, because to know output voltage, I need to know the two input voltages, and one of the input voltages depend on the output voltage itself. These two should be always same. They are short circuited, connected. So how do I get the answer? That's what we are going to look at. Okay. Okay. So let's solve this problem. Okay, let me also draw before that the two power supplies, plus V supply and minus V supply. Okay, to make it more concrete, let's take this as plus 12 volt, let's take this as minus 12 volt. Okay, so this was the question that Vp is known to us, find Vo. Okay, so let me give a value of Vp, say Vp is equal to 5 volt. Okay, so this is 5 volt, these two values are plus 12 volt and minus 12 volt. What is Vo? That's the question, and it's a chicken and egg problem, not so easy, but not so difficult as well. Okay, let's do it here. We have to use the static characteristic to answer this question. So what was the static characteristic? Static characteristic was this curve where we have input versus output of an op-amp. Y-axis is output and x-axis is the difference of the two inputs. So this is Vp minus Vn and this is output Vo, right? And we saw that this curve looks like this. When Vp is greater than Vn, the output is positive. This side, when Vn is greater than Vp, the output is negative, and it stays constant like this on both these sides. And near zero, the value of the voltage gradually changes from the positive to a negative value. Okay, exact shape of this curve is not very important, but it gradually goes from negative to positive. Okay, now let's make a guess what the Vo is. Let's make a guess, so we'll and see is that correct or not. So we will guess that Vo is equal to plus 12 volt. Okay, so Vo plus 12 volt means the point lies somewhere here in this region, right? This is Vo equal to plus 12 volt. Now if Vo is plus 12 volt, then Vn is also plus 12 volt. So if I guess Vo is plus 12 volt, then it implies Vn is also plus 12 volt, right? Because that's what comes here. Now if Vn is plus 12 volt and Vp is given to be 5 volt, so we know Vp is equal to 5 volt. So Vp is 5 volt and Vn is 12 volt. Which one is higher? Vn is higher. Now if Vn is higher, what the output should be? So this implies that Vn greater than Vp, and this implies that the output Vo should be equal to minus 12 volt because Vn is higher. So we started with a guess that Vo is plus 12 volt, but we then see that if Vo is plus 12, then Vn is Vn is also plus 12. That means Vn is higher than Vp, and if Vn is higher than Vp, then the output should be negative, minus 12 volt. Then this is not possible. So then this is not possible. It's not possible. So this is a wrong guess. Okay. We failed. Let's try once again. Guess Vo is equal to minus 12. Let's see. This time it should work. So we are guessing that Vo is minus 12 volt. So now this will imply that Vn is again minus 12 volt, right? Okay, so Vn is minus 12 volt and Vp is fixed. Vp is fixed at plus 5 volt. Now which one is higher? Vp is higher. If Vp is higher, so this implies Vp is higher, and if Vp is higher, then VO should be equal to negative or positive. It should be positive, plus 12 volt, because Vp is higher. Vp is positive, Vn is negative, so this should be plus 12 volt. Again a contradiction. We started with a guess that it's negative, but then we see that in this situation VO should be positive. So this is also not possible. This is also not possible. We failed to get a solution. Okay, now what do we do? So we know that VO is not plus 12 volts, so it's not anywhere here, it's not here, it's not even here, because it's not minus 12 volt. Then maybe the only possibility is this region where the output voltage changes gradually. Okay, so maybe we have to search only in this region. Now where do we search? There are so many possibilities, starting from minus 12 to plus 12. Let's make a guess. Let's make a guess of VO equal to 0. Let's guess 3. VO is equal to 0. Okay, if VO is 0, so VO is 0, so then Vn is 0. And now if Vn is 0 and Vp we know is 5, so which is higher? Vp is higher, and it's so the output should be positive. Now there is a question: is Vp sufficiently higher than Vn? I mean, are we here or are we inside this region? If we think that this 5 volt is sufficiently higher than 0 volt, the gap is sufficient, 5 volt is, then I mean, if it is sufficiently higher, we know that if it is sufficiently higher, then it should be 12 volt. Okay, so if this point is less than 5, this point is less than 5 volt, okay, and this point, this symmetrically other side, if this point is similarly greater than minus 5 volt, so then we see that Vp minus Vn in this case is greater than 5 volt, so it lies in this region, so the output should be 12 volt. Okay, so then again we have a contradiction, so this is again not possible. We started with a guess that output is 0, and we landed up with the conclusion that the output should be 12 volt. So this is again not possible. Okay, so let's make another guess. Okay, so let's try this. Let me just put some concrete value. Say this gap, which you called as the resolution, is around 0.1 volt, which is actually very bad resolution. But for this example, let's take this value as 0.1 volt, and this side this value as minus 0.1 volt. This is a bad op-amp. This 0.1 volt is a bad resolution. It should be it should be near microvolt, few microvolts. So 0.1 volt is a bad op-amp, but let's see what happens. Okay, so now we're making a guess that VO is slightly less than VP. Slightly. I mean, how slightly? Something like, again, let's guess that it's say VO is 4.99 volt. Okay, if that is so, If VO is 4.99 volt, then in the circuit we see again that VO comes to Vn. So Vn will be equal to VO, which is like 4.99 volt, right? And now we see that Vp is 5 volt. So the difference between Vp and Vn is not large, it's very small. It's only 0.01 volt. Okay, so it's something like here. It's 0.01 volt within this region. So this gap between Vp and Vn is within this resolution band, right? So then the output will not be fully positive or fully negative. The op-amp cannot go to full positive or full negative value. Although Vp is higher, the output will not be 12 volt because it's not sufficiently higher. It's only, so this difference Vp minus Vn is only about, say in this case 0.01 volt. See, and this is not a large difference. So the output VO will not be 12 volt, will be rather less than 12 volt. Okay, it will be less than 12 volt. And what the value will be? For that we have to check. So this is Vp minus Vn, which is 0.01. So we have to come at this point, yeah, and we have to see what's the output value here. And it's possible, if you are lucky, that this value is 4.99. It's possible because this value is 12 volt, this is 12, this is 0, and at 0.01 if the curve favors us, then the value can be 4.99, right? And in that case we'll find the solution for VO. So then VO can be or maybe it can be equal to 4.99 depending on the static characteristic, this curve. Right? There is no contradiction, as we seen earlier, that we started with a guess of plus 12 volt and ended up with a conclusion that it should be minus 12 volt, which was directly contradicting our initial guess. In this case we do not see any contradiction, although it doesn't say conformatively that this has to be 4.99, but it gives us an indication that the VO will lie somewhere in this region, right? And I'm telling you, just give it a thought that the VO will actually be slightly less than Vp. Whether it's 4.99 or 4.98 or 4.999999, how close that to Vp, that depends on this curve, right? But the answer and the solution will be that VO is slightly less than Vp. Give it a thought. So the conclusion is that in this circuit, okay, in this circuit the solution for VO will, that solution point will stay in this increasing region of the static characteristic. It will not be in this 12 volt region, which we call as a saturation, where the output is saturated, fixed. It doesn't increase any more, doesn't decrease in this region. So these two regions we call as saturation regions. So that means if we change Vp minus Vn in this region, the output doesn't change anymore, it stays constant. That's why we call it a saturation region. And in this case we are saying the solution will lie in this increasing region, not in the saturation region. Give it a thought. Okay, and take a pause the video, give it a thought, and then come back for later discussion when I share my thoughts or how I think an op-amp behaves. Okay, pause the video. Okay, so I was about to share my thoughts or my thought process about how an op-amp behaves. This is an informal discussion, I will say, because this is more like my thought process than the perfect physics is about the op-amp. So what I thought is like this: if I have an op-amp where I have two inputs, minus and plus, the plus terminal is fed with an external source, but the minus terminal is fed back by the op-amp itself. It's feedback, right? It's feedback. Okay, so in this case, I think like this: if this potential is positive, say 5 volt plus 5 volt, then the output, I think like this. This is not a perfect physics, and I always analyze these things or remember these things in this way. So if this is positive, the output tries to be equal to plus V supply, right? If this is positive, if this point is positive, then the output tries to go to plus 12 volt, which is positive V supply. Now if it is trying to go up, then that voltage is fed back here, right? So this voltage also tries to go up. Again, I'm saying it's an informal thought. Okay, so this voltage goes up, so this point also goes up, and therefore the difference between these two reduces. Let me reiterate. Let me start with the assumption that all the voltages are initially 0. I suddenly connect a plus 5 volt here, then this is still 0. If this is 0, this is plus 5 volt, then the output will try to go towards the positive, extreme positive value. So the output is increasing, therefore this voltage V negative is also increasing, and so what happens, the gap between V plus and V minus reduces, and when the gap is very small, sufficiently small so that we are within this band, in this increasing band, if this gap between Vp and Vn is within this region, then the output stays happily at that value. Okay, it doesn't go up further. So something like this, again, this is informal thought, but to give a picture of it. So if this is plus 5 volt, this is increasing. So say the thing when this is 0, this is also 0. So the difference is plus 5 volt. So when VO is VO, VN, VP, let me make a table, VP, VO, VN, something like that. So VP is always 5 volt. Now if VO is 0, then VN is also 0, then VP minus VN is 5 volt, is super large, it's sufficiently positive, then this will cause the VO to go up because the difference between the two inputs is higher. Now when it goes going up, say it's becoming 1 volt, Vn is then also equal to 1 volt, then this difference will be plus 4 volt. This is still quite high, right? So the VO should, to find the solution for VO, I should increase the value of VO. Now let's try with a value of say 3 volt. Now 3 volt, if VO is 3 volt, then VN is again 3 volt. So VP minus VN is 5 minus 3, 2 volt. This can again be considered as high enough. Let me draw the static characteristic here. VP minus VN along the x-axis, VO along the y-axis, and say this is the static characteristic. So this is 12 volt. This point is minus 12 volt, and let these these two values be 0.001 volt minus, and this is plus 0.001 volt. Right now, so I have, in this case, if VO is 3 volt, I see that I have to increase VO further. So let me make a guess that VO is 4.9 volt. If VO is 4.9 volt, then VN is also equal to 4.9 volt. Then this difference between VP and VN is 0.1 volt, and we see that this 0.1 volt is higher than this 0.001 volt. So I have to increase VO further. I'm just searching for a solution. What should VO be? Now let me try with 4.99 volt. Then Vn is also 4.99 volt, and this gap will be 0.01 volt, and I see that 0.01 is still greater than 0.001. So let me increase it further. Let me try with 4.999. This is also 4.999. So this is then 0.001, and then this point is here. So I still see that at 0.00, when this gap is 0.001, the output should be 12 volt. So I have to increase it further because it's not equal to this. So let me increase it further, and maybe for 4.999949, this is 4.9999. Then this gap is 0.00001. Then that point will be here, and I have to check what is the value here. It's possible that this value is higher than 4.99 volt. So this value is 7 volt. In that case, I have to increase VO further. If this is 7 volt, okay. If this is observed to be 7 volt, then I have to increase it further. And if it is observed to be lower, something like 3 volt, okay, then I have to reduce this. I may have to reduce this, right? So maybe let me continue this table here. VP, VO, VN, VP minus VN, VO as observed in the curve, okay, and then I will take a decision which way I should move to find the solution. So VP is as always 5 volt. So I'm starting with this guess 4.9999. So this is also equal to that. So these two are always equal. So this is 4.9999. So in this case, I see that this is 0.0001. Now I come to this curve and find out what is the value of VO for 0.0009. Suppose this value is 7 volt. Say this point is 7 volt. Let me use a pen. Okay. So this point is 0.0001 corresponding to this value, and the corresponding Y value or the output value here, say this is 7 volt. Okay. So I see that this should be 7 volt, and that means but I am currently at the guess of this 4.9999. So I have to increase my guess. I have to increase my guess further. So let me try with the guess that 4.9999 0.9999959. So here I will see 0.00001. This is the gap between Vp and Vn, and let me zoom it in. Let me zoom in this part. Let me zoom in this part of this characteristic curve. Say this looks like this. This is the saturation region. Okay, so this is the x-axis, this is the y-axis, this is one saturation region, this is another saturation region, and now I see that with this case of VO, Vp minus Vn comes out to be 0.4 zeros and then 1. So I come to that point, this is 10 to the power minus 1, 2, 3, 4, 5, 10 to the power minus 5. Okay, at this point I see what is the value. I see the value is 3 volt, say for example. So if this is 3 volt, but then my current, say this is not, this can be practically 3 volt. Sorry, that's not possible. Say this case, so this value at this point is something like 4.99998. Okay, so I guessed the value to be 4.1234559, but when I put the value here in this curve, I see this value comes out to be 4.1234449 and then 8. So then I have to reduce my guess slightly, and I will maybe try with the next guess as 4.999985, and this way I can keep my search on until I find a point here, so that with that guess of VO, when I compute Vp minus Vn and find the corresponding value here, everything matches. So I have to find the solution this way, right? Okay, so this is how we can do it. So I always think like this, that if I give a 5 volt supply, the output will try to increase until the value is very close to 5 volt, something like 4.999985, until the output is close to that, and then the difference is very small. And if the difference between these two is very small, I am somewhere in this region, in this characteristic curve, where all these things are satisfied. I mean, everything matches on this curve. So what happens? The output goes up and makes itself almost equal to this plus 5 volt, right? So the output is then almost equal to plus 5 volt. And how close to plus 5 volt? That depends on the width of this resolution gap, this gap. If this gap is very small, say if this gap is 0.000001, then you can definitely readily guess that the final voltage here or here will be 5 volt minus something which is less than 0.00001. So it will be very close to 5 volt, right? So this potential will come to this value, almost equal to this value, but not exactly equal, slightly less than that. I hope it's clear. Now let me introduce a new terminology which is called virtual sorting. What is that? In this case, we saw that when you give plus 5 volt, the output goes up and it makes this other input almost equal to this Vp, this positive input. So as if these two terminals, so that means these two terminals are always almost at the same potential, as if they are internally sorted, virtually sorted. Okay, so that's why we call this as a virtual sorting. Now, one thing that you must realize and understand, that virtual sorting is not same as actual sorting. Why? If if we have two terminals which are actually sorted, it's firstly these two terminals will then have. Let me draw this diagram once again. Okay, this is connected to a voltage source, and this is VO. Okay, so actual sorting firstly will imply that these two have exactly same value, but in this case, in this circuit, these two will not be exactly same value, but this will be at a slightly lower potential than this. Slightly. How lower? That depends on this resolution. This resolution, this gap in this curve. But it will be slightly small. Secondly, also know that no current flows from here to here or here to here. I mean, first of all, we know that actually there is no current which goes inside, right? This is the second important property of an op-amp. We said internal impedance of an op-amp is infinite. Similarly, no current goes from here to here, right? So there is no direct connection. This virtual sorting only means that this potential will be always adjusted by the op-amp to make it equal to this potential, but there is no direct connection, as so to say. And okay, this was the plus, this was the minus terminal, right? Now, and the fact that these two are at the same potential is only because op-amp increases its output potential and tries to make it equal to this potential. Now, this is not always true. This is not true. For example, so this was the circuit we discussed so far. Now let's discuss another circuitry. Say we have two terminals. Definitely, one of them is supplied with an external voltage source, and the other one is fed back from the output itself, like this one. But in this case, I take this as the minus terminal and this as the plus terminal. Okay, so instead of feeding the plus terminal with a voltage source, in this case I feed the minus terminal with a voltage source, and the plus terminal is fed back by the op-amp itself. Okay, so in this case, think of it, these two terminals will not have same potential. Okay, so here virtual sorting is not applicable. Why? Let's do the same exercise as we did before. So we want to find out Vu is equal to what? We know this is Vn. Vn is given, right? Say Vn is equal to 5 volt in this case. So this is Vp. Vp is equal to Vo because they are sorted. What is Vo? We don't know. Vn is given. Now we will again make guesses and find out what the solution is. So we will guess the value of Vo, and then the value of Vp, which will be equal to Vo definitely, and then Vn is a constant equal to 5 volt. Then we'll find the difference Vp minus Vn, right? and then from the characteristic curve, from the static characteristic, we will observe VO, the value of VO from static characteristic, and we will make a decision whether our guess value, so this is the guessed value, so we make initial guesses, and then with that guess we check whether the in that point, in that solution point, what is the value of VO output according to the static characteristic, and then we make a decision about how to modify the guess. Okay, so then we'll make a new guess, and we will do it iteratively until and unless we find a solution. So let us first make a guess, something like VO equal to 0, a random guess. Now if VO equal to 0, VP is also 0, these two are sorted, these two are directly sorted, and this is an actual sort, it's sorted with a copper wire. Vn is always 5 volt, then Vp minus Vn is what? Vp minus Vn is 0 minus 5 volt is minus 5 volt, right? Now if this is minus 5 volt, okay, let me draw the static characteristic, input versus output. Input is Vp minus Vn, the difference between two inputs. Here we have the VO output, and the curve looks like this. Here 12 volt, here minus 12 volt, and this gap is very small. Let me take this gap as, say, something like 0.001 minus 0.0012 plus 0.001 volt. Okay, this gap is very small, right? So now, so this Vp minus Vn is minus 5 volt, so it lies somewhere here. Okay, so somewhere here is the minus 5 volt, and at that point we see that the output should be minus 12 volt. So this is minus 5 volt, Vp minus Vn is equal to minus 5 volt, this point, and here we see that the output should be minus 12 volt. If so, this should be minus 12 volt. Okay, so we started with a guess of 0 volt and found that the VO should be negative. So we modify our guess. We modify our guess that try with a lower value of V. How lower? Let's try with minus 2 volt. Okay, if this is minus 2 volt, then this is also minus 2 volt, then this is always 5 volt, then so Vp minus Vn, so this is Vp is minus 2 and Vn is 5, so minus 5, and we see that this is equal to minus 7. Okay, so now what is the value of VO at minus 7? So this was minus 5 volt, so minus 7 is somewhere here, and there also again the output voltage should be minus 12 according to the curve. So that means we are guessing it to be minus 12, but we are finding that it should be we started with minus 2, and we see that according to the curve at this point it should be minus 12. So we have to lower our guess further. Okay, let's lower it to minus 8. I'm taking a large step here. So let's guess, just a guess, that this is minus 8, then this is also minus 8, this is always 5, and if so, then this is minus 8 minus 5, this is equal to minus 13, and at that point minus 13, this should be again minus 12. So minus 13 is somewhere here towards the extreme left, so we should get a value of minus 12. Okay, so what will happen? We have to reduce our guess further. Now next we make our guess as minus 12. See the output. We are guessing. These are guesses. GUESS. Okay. So these are the guesses. This column are the guesses. So we are guessing minus 12 volt, and then if so, this is also minus 12 volt. This is always 5, and then we'll have minus 12 minus 5 is equal to minus 17 volt. And again on minus 17 volt we have to we'll see that this is minus 12 volt. So we see okay, we got the solution. We are happy now. So we started with the guess minus 12 volt, and we see that the output should be minus 12. Okay, so we are happy. We got the solution. So the solution is VO is equal to minus 12 volt, because when we start with that guess, VO is minus 12 volt, we see that VP is minus 12, VN is 5, the difference between the two inputs is minus 17, and at that point, when the difference is minus 17, the output is minus 12. Yeah, so we are happy. So our guess and the value from the characteristic curve, they matches, they are equal. We are happy. We got the solution. Excellent. So what we see that this is the solution. In this circuit, if we give plus 5 volt here, the output will be minus 12 volt. Minus 12. Okay, and this situation we call as a saturation situation, where the output is going to the minus saturated values, extreme possible minus value. Okay, it cannot in an op-amp, the output can never go beyond the range of this plus V supply and minus V supply, which is 12 volt in our case. So the output cannot go beyond plus minus 12 volt. It is always between plus and minus 12 volt. Okay, so this we called as a saturation situation. And in this case, we see that this is 5 volt, this is minus 12 volt, and these two are not equal. So here virtual sorting is not applicable. What is the difference between these two circuits? Here the virtual sorting was applicable, and in this case we gave the supply at positive terminal and the feedback at negative terminal. In this case the supply is at negative terminal and feedback at positive terminal. Here virtual sorting is not applicable. Here virtual sorting is applicable. Okay, so that's about the op-amp. In this video we'll come back with exciting uses of op-amp, how to make useful circuits with op-amp, amplifiers, etc. in the next video. Thanks for your patience and watching. Bye.